Hello and welcome back. In this video, we're going to be talking about how we go and apply exponentials. The real life scenario that we're talking about in this particular case is actually a bushfire, okay? Right now, bushfires can experience exponential growth because it can start from a small point and it burns more, creates a wider fire front, which then allows more to be burnt at the same time, and then so forth. Okay, so that's why we can apply an exponential model to this particular example. Okay, so a couple of things that we want to do before we do anything else. We want to unpack in terms of what's happening in the question. So here's our rule. A is equal to 5 times 1.22 to the h. Okay, noticing that our unknown, I'm going to highlight this, is actually in the power, so it's an exponential. Noticing also our units, A is in hectares and H is the time in hours, okay? All right, so we're going to dive straight into it in terms of what's happening. The first thing that we want to look at is what was the initial area burnt? So to find the initial area burnt, that happens when we have had no time pass. So we would say when H is equal to 0, we've had no hours occur. We plug that directly into the formula. 5 times 1.22 to the power of 0, okay? Right, we then plug that into our calculator and we should end up with 5. You may notice straight away that the initial area burnt, rather conveniently, is also the number out the front of the exponential function, and that's because your initial point on an exponential curve is where we have the y-intercept. We can't have negative values in models like this because we can't have negative time. Okay, so 5 hectares should be the initial area burnt. That's where we are starting our model off. The fire's been going for a little while. We're saying at time 0, we have 5 hectares burnt. Part B. What area to the nearest hectare was burnt after 3.5 hours? So in this particular case, we're just letting H equal 3.5. Okay, we're going to round our answer to the nearest whole number for this. Okay, you don't have to, but we just want to understand it. So we plug in, okay, 3.5 hours, 5 times 1.22 to the power of 3.5. Okay, and you'll come up with 10.03 with a couple of extra decimals, which is just equal to 10 hectares to the nearest whole number, the nearest hectare. Okay, so that's all fine and dandy for the moment. There's nothing too complicated there. Where we throw a spanner in the works is what happens when we have 20 hectares burnt and we want to find the number of hours. Inside of standard, we don't have any logarithmic or logarithmic techniques to help us out when solving equations. But essentially what we're trying to find is where our equation, our A value, okay, is actually equal to 20. So our 5 times 1.22 to the power of h. And we're trying to find what value of h that occurs for. There are a couple of different ways that you can go and do it. One of the most prominent ways that I see students do is guess and check. Okay, which is quite useful when you need large values. The other option is to do a table of values, which can sometimes be quicker in terms of just plugging them into the rule. Okay, so for your table of values, I've gone through how to use table of values with exponentials in earlier videos, so I'd encourage you to probably rewatch those for you to use a table of values. I'm just going to fill in our table of values here, and you'll notice what's happening. We're after the numbers in this row to be equal to 20. Now, where do you stop? You stop once you hit the number of 20. I've just included a few. I'll stop filling it out once we get there. So when h is equal to 0, we have 5. We've already done that. When h is equal to 1, you have 6.1. When you have 2 hours, 7.4 hectares have been burnt. Noticing here, I might just pause and just show you this. I've got x and y here, just so you can see that they relate to the coordinates. But in terms of this, what we're actually writing, okay, is actually H for the hours and A for the area, okay? All right, so continuing on, at 3 hours, we have 9.1, and we expect that based off of the answer to our last question, okay? Going for 4, we end up with 11.1 hectares burnt. At 5, we're getting to 13.5. So we're not at 20 yet. The next one is 16.5, and then the next one is 20.1. So once we hit 7 hours, we're going to have 20.1 hectares burnt. So we would say after how many hours? We would say approximately 7 hours, okay, for 20 hectares of land to be burnt. Okay. All right. So I have in this particular question, graph the function for values of h from 0 to 6. Noting that we have our table of values here, you can get on some grid paper and go and graph that. I'm going to use the speedy graph method, noting that this is not going to be absolutely perfect, but I'm going to use the speedy graph method to go and graph this out. Okay, the first thing that we go and do, we create our Cartesian plane. Okay. Now, noting that your pencils and pens will not be able to create a perfectly ruled line straight away. Okay, and I should be using the labels of H and A in this particular case. So, like before, we find our y-intercept. We know that that's 5, and we're going to place a dot there. Okay, at 5. Next thing, I need a reference point. I can pick whatever numbers that I would like. It's completely and totally up to you. I'm going to use up here the value of 2 and 7.4 just to create a reference point, just so I can differentiate it. Okay, so I'm going to put another dot here at the coordinate 2 and 7.4, noticing that it doesn't have to be exactly to scale. I'm just establishing a bit of a pattern here, a little bit of a way to analyze what's happening with our curve. And now I go and graph my exponential curve, connecting those two dots and ensuring that I approach the horizontal axis. Okay. All right, but don't quite touch it due to the asymptote that's going along here. So you should go and use a different colored pen if you can, and just add in a dotted line to remember that asymptote. Okay. All right, we knew that it was a growth curve as well. I didn't actually specify that. When we look at the particular power for the rule, the power is positive. Now, 1.22 is a fraction. However, it's a fraction bigger than 1, so we don't do the opposite, okay? So we've ended up with our curve being here, okay? And you should label your curve. It's always a good practice in case you have multiple curves on the same graph. Now, your graph will obviously be a little bit more detailed than mine. However, I've gone away to a graphing calculator, which is known as Desmos, and I've graphed it out neatly for our next question. Okay, you can do the same, or you can use, if you have my worksheet, you can use that to go and plot everything, because quite often in the HSC, you'll be provided with a graph. So for example, in this particular question, it says, use your graph. So if we're going to use our graph, we want to make sure that it's really, really accurate. Okay, first thing that it says to use this graphically, we can do some of this with algebra with the guess and check method, or with just substituting in. After how many hours will 10 hectares of land be burnt? Noticing that on our y-axis we have A, and on our horizontal axis we have H. So what we want is we want to use a ruler here to be accurate, okay? All right, so we are going to come across here from 10 for our area of our hectares, because that's what we're after in the first question. And we're going to come across until we end up meeting our curve, which we meet it right here. Okay, if your graph isn't like from Desmos, it may not be perfectly accurate. Then we're going to come down here, okay, following it until we end up with the middle of 3 and 4, which is 3.5 hours. Okay, so we know that it'll take 3.5 hours for that to be burned. I want to draw your attention that we've actually already done this question algebraically. Okay, up here, what area to the nearest hectare would be burned after 3.5? And we ended up, okay, rounding to 10. Okay, so this is just visually confirming what's happening with our curve. So for part B, we're after the area burnt from 5.5 hours. So now what we're going to do, we'll do this in purple. We're going to go to 5.5 hours on the horizontal, okay, and we're going to draw up until we meet the curve, and then we're going to go across to the hectares. Now, you'll see if your eyes are faster than my drawing without a ruler here, okay, that we end up here at 15 hectares being burnt in that time, right? So we would say approximately 15 hectares. We can actually confirm that by substituting into the formula. So for example, I'll just come down below. When we have 5.5 hours, we have A equals 5 times 1.22 to the 5.5 on your calculator, that will come out to be 14.9 hectares, which is really, really, really close to what we have graphically, okay? All right, noticing that due to the thickness of the line, it's not exactly going through what we are after, okay? All right, so we know that our graph confirms what's happening algebraically. Finally, a really, really common style of question asked in the HSC is what are the limitations of the exponential model? So in this particular case, you'll notice that the curve keeps going up and up and up and up and up forever. However, that's not how it works in real life. You can't have a bushfire continuing to grow forever because eventually a couple of things are going to happen. You could have firefighters meet it and put it out. You can run out of space for the bushfire to grow into, for example, a less dense vegetation, which a better way of saying that is actually that the bushfire runs out of fuel. So you won't have a curve going up forever. Eventually, at some point, it will have to peter off and then stop completely. Okay, so any of those reasonings is fine. Okay, but the model assumes, and here's how I'd write it, the model assumes that the area will grow and never stop, but fires eventually run out of fuel. Okay, and that's all that you need to answer for that. So that's how you go and apply exponential models to real life scenarios. And they do have limitations, but they are just there to sort of help us gain a little bit of an idea of what's happening in the short term. Okay, all right, thank you very much.